Okay, well, I would like to start by thanking the organizers for inviting me to come here. It's really indeed an honor to be here at a conference in honor of Alexander Oparin. So I'm going to try to do two things with this talk. My advertised title is to do something entirely different than what we've been hearing about. I've been hanging around with astronomers a lot over the last few years, and so I want to give you a different approach for trying to find out about the origin of life. But before I do, I just want to react to a couple of thoughts that have come up earlier in the conference, in fact, earlier this morning. The first has to do with the composition of the early atmosphere and whether or not compounds in the early atmosphere could serve as a metabolic energy source for early organisms. We heard about hydrogen from Mikhail Fedonkin and also from Elisabetta this morning, but we also heard from Elisa that carbon monoxide, CO, can be a useful metabolic energy source for many types of organisms. And I want to plug carbon monoxide because one of the things that we do in my group is we make theoretical models of atmospheres, including the Earth's prebiotic atmosphere. There's many uncertainties as to what that would be like, but here's this slide shows a typical representation from a computer model calculation. This is for a 1-bar atmosphere that has about 20% CO2 to counteract the faint young sun. The sun, we think, was about 30% less bright, so you need greenhouse gases. We heard about hydrogen. This came up during Fedonkin's talk. Hydrogen in this model is a little less than 0.1%, not the 30% that the Tien et al. Paper predicted. So that's still enough hydrogen to be very useful. Methanogens can use it to make methane once they evolve. But notice that there's also carbon monoxide in this atmosphere, and that's what I want to emphasize. The carbon monoxide, some of it comes out of volcanoes, but there's a peak up here in the stratosphere because carbon monoxide is produced from photolysis of CO2. And there's a quantum mechanical quirk that carbon monoxide does not recombine rapidly with atomic oxygen to reform CO2. So consequently, you get quite a bit of CO in these atmospheric models. Hydrogen comes out of volcanoes also, but hydrogen escapes to space. And so what that means is that CO builds up in excess compared to hydrogen. So what does that mean for metabolism? Well, here's a reaction that Elisa put up earlier. The CO plus water goes to CO2 plus hydrogen. This reaction is actually very well known, not just to biologists, but to chemists. It's sometimes called the water-gas shift reaction. If you take that model atmosphere that I just showed you and do a thermodynamic analysis on that, the Gibbs free energy that you can get is, of course, it's the Gibbs free energy for the standard state, which Elisa showed you is very small, but then you get this term from the product of the reactants divided by the products divided by the reactants. And this, for that particular model, comes out to about 17 kilojoules per mole, which is quite a lot. That's about half the energy that you need to synthesize ATP from ADP, and it's well in excess of the amounts of energy, 10 to 15 kilojoules per mole, that can be used by many anaerobes. So at any rate, the point I'm trying to make there is that CO should have been an abundant compound, not just in hydrothermal vent systems, but also in the atmosphere. So that's a good thing to look at for early organisms. Then the other idea that I wanted to react to was this question about the hydrothermophile ancestors. What does that mean about the environment? Well, there seems to be a common impression that the early Earth was hot. And where does that come from? Well, it basically comes from studies of oxygen isotopes in ancient rocks, particularly cherts, which is SiO2, and carbonates. And when you go back to the Precambrian, the cherts are better preserved. So there are geochemists who look at 018 to 016 ratio in ancient cherts. Paul Knauf at Arizona State is one of the people that has done this for many years. I don't know if you can read his graph. This is from a 2005 paper, but this is delta 018, related to the percentage of 018 in the cherts versus time. And this envelope here, these are the data, the points here, and if you, that's increasing delta 018 this way. More delta 018 means low temperatures. So you can see that there's a downward trend as you go back in time. This is the boundary between the Archean and the Proterozoic. And the Archean in particular, prior to 2.5 billion years ago, looks very warm if you take these 018 data at face value. In fact, the published value that Paul Knauf and Don Lowe put out in another paper a couple of years before this was 70 plus or minus 15 degrees C. Well, that agrees with what you heard from Dr. Yamagishi's talk this morning. He taught, well, this afternoon. So he talked, showed you some studies of different compounds, biological compounds, enzymes that are thought to be ancient. And Aki mentioned this paper. There were two papers by Eric Gaucher et al. This is a figure from the 2008 paper. What Gaucher et al. Did is very similar to what you heard about this morning. They sequenced a variety of organisms and looked at genes coding for different elongation factor proteins. And then they tried to figure out which genes were ancient. They synthesized the corresponding proteins, and then they measured the melting points of those proteins in the lab. And so this is very similar to what you just heard. They went one step further than that. They used molecular clock data to try to figure out when these different organisms, when these proteins existed, when the organisms that hosted them existed, and then those are plotted. This is now time here in billions of years before present, and this is temperature in degrees C. These bars here represent the melting temperatures for these different proteins, and this dim gray curve here is that those are the temperatures inferred from the oxygen isotope data in cherts. So they plotted those right on top of each other, and the agreement looks very good. So if you don't know too much about this, you might be very convinced that this then represents the temperature history of the Earth based on two independent sets of data. But I just want to point out that there's another set of data that to me is actually more compelling, and that's the glacial record of the Earth. So here it is, just without going into detail. There are ice ages that go way back in the Earth's history. You know, we're still in an ice age actually right now because we have ice on both poles. But if you go back and look at the Precambrian here, there were some very deep ice ages at the end of the Precambrian, around 600 or 700 million years ago, when the Earth may have frozen over entirely. There was an ice age. Apparently, this is one that has only recently been reported at about 1.8 billion years. There was a series of at least 3 ice ages at 2.5 billion years when oxygen first rose. And we've argued that that's because the oxygen rose and that decreased the methane concentration of the atmosphere, and methane's a greenhouse gas. So that may have triggered that glaciation. Whoop. So there are also ice ages in the mid-Archean here at 2.7 and 2.9 billion years. And the chert data by comparison suggests that the mid-Archean was still warm, 60 or 70 degrees C. So one of those data sets has to be being misinterpreted. I tend to put more faith in the glacial record because there's less interpretation that goes into it. So the bottom line of that would be that the Earth may have been very hot back here in the Hadean and the early Archean, before the rock record really gets going. But by the late Archean, the Earth was almost certainly cool, probably not much hotter than today. so let me then switch to back to my advertised topic. This is what I think is actually maybe a very good way to look at the origin of life problem. You know, I love going to origin of life meetings because the origin of life to me is the most difficult and maybe the most interesting scientific question. But it's hard to make progress on it, and one way to make progress is to try to figure out whether it happened more than once. That's really what the whole field of astrobiology is about. Astrobiology is the search for life off the Earth. Most astrobiologists that I know are interested in looking for life within our own solar system, either on Mars or more speculatively on Saturn's moon Titan or on Jupiter's moon Europa. What I want to talk about is the idea of looking for evidence of life on planets around other stars. So that sounds even more speculative, but what I'm going to try to convince you is that that may actually be easier to do than looking for life within our own solar system. Now, if we're going to look for life on very distant exoplanets, we call these planets, you first have to decide what it is you're looking for. We've heard several definitions of life at this meeting. Here's one that I've attributed here to Jerry Joyce, but this has been, I think, written down by a number of different people. So this definition is that life is a self-sustained chemical system capable of undergoing Darwinian evolution. And I like that definition. NASA likes that definition because it's very general. It doesn't presume anything really about the physical characteristics of life. And so it doesn't preclude having life on a place like, say, Saturn's moon Titan, which is very different from the Earth. But it's also not practical for astronomers, because astronomers are interested, as I said, in looking for evidence of life on planets around other stars. And this is not, you know, this is a definition you could test in the laboratory. If, for instance, we went to Mars and brought back a sample of rock, we could then analyze it in the laboratory and look for something that satisfied this definition. But you can't do that from remote observations. What can we look for? Well, what you can look for remotely is the byproducts of metabolism. And this is also not a new idea. Many years ago, back in 1965, James Lovelock published a paper in Nature suggesting that the simultaneous presence of oxygen and methane in a planet's atmosphere would be very strong evidence for life. These gases are way out of equilibrium with each other, out of thermodynamic equilibrium with each other in Earth's atmosphere. There was a paper that actually came out earlier that same year by Joshua Lederberg, who was a Nobel Prize winner, which had a very similar idea. He suggested that extreme thermodynamic disequilibrium in a planet's atmosphere could be evidence for life. I'm not actually sure that that generalization works, but Lovelock's original idea of oxygen and methane is probably a very good one, because it's very difficult to imagine how you can get an abiotic planet that has high concentrations of both of those gases. Well, the question is then, can you look for something like that in the spectrum of an Earth-like planet? Here's the spectrum of the Earth, and this is with an exoplanet, what astronomers hope to be able to get is a single pixel spectrum, because I'll show you in a moment, they want to be able to separate out the light from the planet from that of the star, but you won't get any spatial resolution. You'll only get a spectrum of the entire planet. So the astronomers wanted very much to get a single pixel spectrum of the Earth. That turns out to be difficult to do from Earth orbiting satellites because they're too close, and so you get spatial resolution. Well, instead of, there were suggestions that we should put a space telescope out at the Earth-Sun L1 Lagrange point in between the Earth and the Sun and point it back at the Earth and get a spectrum that way. That would have been fairly expensive, $20 or $30 million. Fortunately, a few astronomers at University of Arizona came up with a cheaper way to do it. They went up on Kitt Peak, where they have a telescope right near the university, and they turned the telescope on the moon. Here's a picture of the moon in crescent phase. You can see, if you go out on a dark night, you've probably seen with your own eyes, you can see the dark side of the moon, not just the bright side of the moon. Well, why is that? It's because there's sunlight that hit the Earth, bounced off the Earth, hit the moon, and then it's reflected back to the Earth. So it turns out that if you take a spectrum of the dark side of the moon, and then subtract the spectrum of the bright side, of the sunlit side of the moon, that gets rid of the moon spectrum, and you're left with a spectrum of the Earth, a single pixel resolution spectrum. So here it is, the black curve here are the data. This is the wavelength scale in angstroms, which astronomers like. An angstrom is 1/10 of a nanometer. So the visible here is from 4,000 to 7,000 angstroms. This is the near infrared over here, beyond 7,000 angstroms. This red curve down here is a model fit to the data. And what you can see is that if you look here in the mid-visible, there's a very broad band. That's due to ozone. That's not the band that we were just talking about in the previous talk. The ozone also absorbs more strongly in the ultraviolet, but it absorbs weakly in the visible, and you can see that in the Earth spectrum. You can also see absorption bands of water here. So that's a water absorption band here at 0.7 microns, and here's two more water bands going out into the near infrared. What's more interesting, though, and maybe more useful in looking for life, is this very deep band right here at 7,600 angstroms, or 760 nanometers. That's the O2A band. That's an absorption band of molecular oxygen. It's actually a forbidden transition. It's not supposed to happen quantum mechanically, but it does happen at a slow rate. And since there's so much oxygen in the Earth's atmosphere, you can see it very easily if you have enough resolution to pick out that peak. So that's something that we would almost certainly want to look for if we were able to get the spectrum of an exoplanet. Notice that you can't see methane in this spectrum. Methane actually absorbs in the visible all the way down to about 5,000 angstroms. It absorbs all the way through this region more and more strongly going into the near infrared, but there's only 1.6 parts per million of methane in the atmosphere as compared to 21% oxygen. So you would actually need a much higher resolution spectrum to be able to see the methane in Earth's atmosphere. All right, well, just to get to the punchline quickly, how would we look for this on an exoplanet? There are, probably the best way to do this is to build a big space telescope, which you would not put in Earth orbit. You need a telescope that is out far enough from the Earth that it's not circling the Earth. There's a point in space called there are these points of neutral stability called the Lagrange points. And if you go to the L2 Lagrange point, which is about 1 million kilometers beyond the Earth, away from the sun, that's where these big telescopes would go. NASA has studied a couple of different concepts. They call them terrestrial planet finder telescopes, TPF telescopes. The C here is for coronagraph, and the O is for occulter. So these telescopes, what you're trying to do here is to see a very dim planet next to a very bright star. And so that means that you need to block out the light of a star and see the very dim planet right next to it. There are two ways to do that. One is by blocking out the star's light within the telescope. So that's called a coronagraph. And that comes from instruments that have been used to look at the sun and block out the disk of the sun and see the hot corona around it. The other way to block out the starlight is to put a disk out there between the telescope and the star, and then you can block out the starlight just like I'm blocking out that ceiling light with my hand. So that's two ways. In both of those cases, you'd be looking at reflected light from this planet that was originally coming from the star. Then there's a third way to do this. TPFI, the I stands for interferometer. You can actually go out into the thermal infrared at longer wavelengths, and the advantage of doing that is that planets are brighter relative to their stars in the thermal infrared. But the disadvantage is that you need a very big telescope. So here I neglected to mention the size. To do one of these visible telescopes, the TPF type telescopes, you need about a 4 to 8 meter mirror. That's quite a bit bigger than the Hubble Space Telescope, which was 2.4 meters. To do the same thing in the infrared, you would need about an 80 meter mirror. And that's, of course, too big to send up as a single dish, but you can get the same effect by flying multiple spacecraft and combining the beams, keeping track of the phases. So that's called interferometry. NASA has a version of that called TPFI, and ESA, the European Space Agency, has studied this actually harder than NASA. They have a proposed mission called Darwin, which would do this. That's the good news. The bad news is that these missions are very expensive. They would probably cost $5 to $10 billion. Right now, neither NASA nor ESA has enough money to pursue this. You may know that NASA is in the process of building a very big space telescope called the James Webb Space Telescope, which is going to be a 6.5 meter telescope operating in the visible out to the near part of the thermal infrared. So that's a big telescope, but it won't do this job because it can't separate out the light from the star from that of the planet. So the James Webb Space Telescope may be able to see some exoplanets, but only if they pass directly in front of their star. It has to transit the star. So there's some sort of faint chance that we may be able to see an Earth-like planet with JWST, but to have a better chance of doing that, we need to build one of these missions. Okay, well, what kind of planets do we want to look for? Let me just briefly say, what life needs. We think that life needs at least 2 or 3 things. I think the most fundamental requirement for life is actually that you need a stable surface on a planet. If you have a gas giant like Jupiter, then there's no surface, no stable surface, so there's no stable pressure temperature regime where an organism could originate and evolve. Carl Sagan was more optimistic than I am. If you've ever read Cosmos, you'll know that there's a diagram in there where he proposed these balloon-like creatures that could live in Jupiter's atmosphere and maintain their height in the air column by adjusting the pressure of this vesicle inside the organism. But that would be a highly evolved creature, and we think that would be very difficult. So the bottom line is you probably need a rocky planet like the Earth. You also need carbon. All life on Earth, of course, is carbon-based. My suspicion is that life anywhere is carbon-based because carbon makes much more complicated chains than other molecules. Silicon is right below carbon in the periodic table. It's mentioned in many science fiction novels as a possible basis for life. But silicon bonds very strongly with oxygen, and it forms things that we call rocks. So once you form a rock, it's very difficult to separate out the bonds. So I think that's also likely an absolute requirement for life. The more controversial requirement is liquid water. And most of you are biologists, so you know that all life on Earth requires liquid water at some time in its life cycle. Some organisms can get by without liquid water for long time periods, for example, by forming spores, but in order to reproduce and metabolize, they have to have liquid water. So I'm going to assume here that we're looking for planets with liquid water, and I'm going to make one further assumption, is that we need to look for planets that have liquid water at their surfaces, because there may be planets, think of Mars in our own solar system. Mars almost certainly has liquid water at depth underneath the crust. There's ice on the surface and there's geothermal heat coming out. So if you go down a kilometer or 2 in the crust, and maybe shallower than that, I think Professor Yamagishi, he's more optimistic than I am. He thinks you might find water near the surface. But the advantage of having the water right at the surface is that you can then have a thriving photosynthetic biosphere as you have on Earth, And so you need a lot of life there to modify the atmosphere in such a way that you can see it. Mars could have subsurface life, but if it does, it doesn't modify the Martian atmosphere in a way that we can detect the life. All right, so this leads me to the concept of the habitable zone, which is something that I've worked on and off for 20 years or more. The habitable zone is defined as the region around a star where a planet can have liquid water on its surface. And that's is shown here. This is an old diagram of the habitable zone. These are different stars. This is the mass of the star relative to the sun. So here's the sun. As I said, it's an old slide, so there were 9 planets in the solar system at the time this planet was made, or this slide was made. Earth is the third rock out, and so Earth is in the habitable zone, and Venus and Mars are just outside it. All right, well then, what the astronomers want to do then, to look for life, is they want to see whether there are rocky planets within the habitable zones of nearby stars. They've defined a parameter that they call ADAS of Earth, which is the fraction of stars that have at least one rocky planet in their habitable zone. Turns out that's what you would need to know in order to design one of these TPF-type telescopes. And so the astronomers have been busy trying to calculate ADAS of Earth. For those of you who have been following it, NASA has had a very successful space mission called the Kepler mission, which was launched in 2009, and it took data up till about April of 2013. It then lost one of its reaction wheels, so it can't really point effectively now, but it has 4 years of data. Kepler is looking for transiting planets, planets that pass right in front of their stars, so that you just see a slight dimming of the starlight. The amazing thing about Kepler is that it was monitoring 160,000 stars simultaneously, looking for planets as small as the Earth. And this is just, it stared at a particular patch of just off the Milky Way for 4 years there, trying to find these transiting Earths. This was an early, about halfway through the Kepler mission, they had already found some 2,300 planet candidates that they call them candidates because they're not verified. They classify them in terms of their radius. R sub E is the radius of the Earth. If the planet is less than 1.25 radii, it's called Earth size. Super Earths are 1.25 to 2 Earth radii. A 2 Earth radii planet is probably about 8 or 10 Earth masses. And we think that that's roughly the upper limit for rocky planets. If they get much bigger than that, they turn into gas giants. So if we're looking for life, you want to focus on the Earths and the super Earths. This is just a more recent diagram showing the same thing. Most of the planets that have been found are Neptune size. That's 2 to 6 Earth radii. That's the big bar here. There are fewer Jupiters and super Jupiters. That's almost certainly real because those big planets are easier to see. It looks like there are fewer super Earths and Earths, but that may not be real because the small planets are more difficult to see. And actually, statistical analysis suggests that there are at least as many Earths and super Earths as there are Neptunes. And then finally, my last data slide, people have been trying to calculate ADAS of Earth using the Kepler data. This was a paper that came out last fall by Eric Pettigura and colleagues, and I won't belabor it because I'm almost out of time, but this is stellar light intensity here in terms of Earth's flux, and this is planet radius. This green area here is the habitable zone according to these authors, and the red dots are the Kepler data. You can see that there's a handful, maybe 12 or 15 planets that fall within the habitable zone. And so from that, Pettigura et al. Calculated that ADAS of Earth is 0.22, suggesting that about 20% of sun-like stars have a rocky planet like Earth in the habitable zone. And actually, for smaller stars, that number may be even higher. So let me just leave you then with 4 conclusions from this talk. First, that CO could have been important, as I mentioned. Second, that the Earth could have been hot early, but it cooled down by the late Archean. Third, that Earth-like planets are probably reasonably abundant. And fourth, that in order to figure out whether life is out there, we need to invest the money and build one of these TPF type missions. If we succeed, whether we succeed or not in finding life, we can answer the question of whether the origin of life is a likely event or an unlikely event. And that, I think, will help us enormously in figuring out how it happened. Thank you.